Recording. All right. So again, good afternoon, guys. I'm glad that some of you remembered that even though it's holiday, I was going to give a lecture because you have a lab tomorrow. So all three of you, very good, good job. Again, it is since it is not required, so those who are not here is also fine. They will be listening and can review tonight or tomorrow before lab. And that's how it is set up. I think similar thing we are going to have later this month also. There are few Mondays off, and there is one Tuesday also off. So I will do based on that, and I will announce if there is a difference between that. Uh, anyhow, so let me begin sharing the screen, and here it goes. Enter screen, allow. Here, screen is being shared. You are able to see that. So today's lab is going to be, tomorrow, today meaning tomorrow's lab is going to be a column chromatographic technique. You will learn yet another new technique. And this one, let me write it down first. So column chromatography. So that is the name of the technique. This is actually a full-blown technique of what you have learned in Organic 1 lab as adsorption chromatography using simply a pipette, which was kind of a childish toy, playing with toy type of thing. This time you are going to be doing with something very professional and something research grade, and you will be doing that a lot in in a research lab. Uh, uh, however, the principle is actually the same. Those who were with me for 262 lab last semester, I have discussed that principle to some extent, and this time we are going to cover very much in depth and the whole thing. Uh, in a sense, some of them are repetitions, but let's do that anyhow. So first of all, why you do that? Anything you learn, your first question comes to your mind is, why are we learning this? What are we going to learn and why? Right? So you're learning a separation technique. So this technique is actually a separation technique. You can separate, separation technique. So this technique is extremely efficient technique, and you can get compounds separated and get extremely pure form of each component from a mixture. So that's that. So that is in fact goal. Goal is to separate compounds from a mixture. That's why it is separation technique. Now, the technique, a column actually looks like this. I'll show you quickly, and then we'll break out into our details. Here is a real column. You see on the left and right, both of them shows a column. Right side is more of an advanced phase in the sense column separation in progress or has occurred. On the left is a similar setup. On the top is a little bit weird. It has some additional thing, not necessarily will be done that way. It can be just open column. Here you also see similar other columns. So column is just a dumb glass cylinder. Okay, a column. The name column is a column which is it's not building column, but it's a glass cylinder. But the glass cylinder has a stopcock at the bottom. As you can see at the bottom has a stopcock, meaning you can actually uh, you can close as well as open the flow of liquid that comes through it. And so it's a vertical column fixed with some some handles or clamps, and something goes inside. We will discuss more about that. Let me also indicate in the context of what, as it says in the separation technique, what are we separating and what is our application aspect. The application aspect is actually you will be able to separate a natural product. A natural product, actually, mm, we have a choice of one from two choices. So the compound that some of you are going to be separating, this compound is called carbon. Carbon. Let me draw the structure of carbon. Here is the structure of carbon. It has 6 cyclohexane ring, a double bond. It also has carbonyl group, a ketone group on this side. But most interesting part is this compound also has a chiral carbon. Here, this is a carbon. Here it has a methyl, sorry, there is a methyl group coming out of it, and here is a carbon-carbon double bond. And on this, here is a hydrogen. So you can see there is a chiral carbon. This carbon is a chiral carbon. So it's an optically active molecule. We have a polarimeter. You should be able to measure optical property, meaning its specific rotation. I have been asking TAs and what is it called, the SCLT Kunga, to make sure you're able to do that. I hope they let you do that. So the molecule is chiral, and this molecule, the one in this stereochemical configuration, that one is R, and it is minus carbon, CarbOne. And it has an optical property. Optical property you have learned in organic 1, that is characterized by what is called specific rotation. Specific rotation. The term is specific rotation. Specific rotation, the word has a symbol. The symbol is pretty strange. It's an alpha, and it has a D. That D represents the light that is used. Actually, it is called sodium D line. Sodium lamp produces various radiations. One of the monochromatic radiation is called D line. So this is that D. And usually also indicated with the temperature, generally room temperature 25 degrees. This entire symbol indicates specific rotation, nothing else. And its value for this R minus carbon is 61 degrees. Now, if you have to imagine, since it is a chiral molecule, it is going to have a stereoisomer and enantiomer. And look what the enantiomer is going to look like, just a mirror image. So let's try to draw the mirror image structure. Here I am doing in that manner, double bond toward the mirror, and carbonyl group away from the mirror. The hydrogen is sticking, it is away toward the mirror, and here is the solid, means toward you. This is I wrote hydrogen, and toward you is that same group, carbon-carbon double bond, and it is a methyl group. So that is its uh, enantiomer. So what would that name be for this enantiomer? You guessed it. It is going to be its. If that one first one is R, this is going to be S. If first one is minus, this is going to be plus. Same name, right? Because it is its enantiomer. So what is going to be its specific rotation? What is going to be alpha D25 value? Can you guess? Well, it is going to be the same number, just opposite sign, right? It's plus, so it is going to be positive 61 degrees. So that are two things. However, here is the interesting part. These two compounds, the source of these two are not the same. Okay, the first one is found in spearmint oil. So spearmint flavor that you get in many flavoring agent, as well as some mouth freshener, etc. Spearmint oil. Spearmint oil has 50 to 80%, depending on its origin. Can 50 to 80% is spearmint oil. Spearmint oil has 50 to 80% of R minus carbon. And the plus one, The dextrorotatory one, that one is not found in spearmint oil. That one is found in caraway seed. Caraway seed. So nature selectively picks one enantiomer, not the other in its body. And that one, caraway seed oil, has about 60 to 70% of carbon, or is plus carbon. So plus carbon is in caraway seed, or minus carbon is in spearmint oil. So these two are enantiomers, right? You understand enantiomery concept. Their relationship is that they are enantiomers. So you are going to be, in fact, the plan is half of the class, since we have two separate labs, it's quite possible. One lab is going to be doing this spearmint oil. Other lab, on the other side, they are going to be doing the caraway seed oil. So we have two different things, but and they will have their own separation product. So as you know, the enantiomers have the identical physical properties, right? Enantiomers have the same melting point, boiling point, refractive index, same IR spectrum, same NMR spectrum, everything same. Since it is a uh, as you see, two pi bonds are conjugated, it will have an UV spectrum also. That will also be the same. What is difference? Difference is in their optical property. One rotates plane polarized light in the negative direction, meaning counterclockwise. Other one rotates the plane of the plane polarized light in the clockwise direction. The one that rotates clockwise direction, that is dextro, that is plus. Okay? And you can also see R has nothing to do. R is a man-made configuration. Similar to IUPAC, this one is given by few people. I think you have seen that in Argon, Can in gold, Prelog configuration, also called this one. So the boiling point is also the same. In fact, their boiling point for all of this, if I write here, boiling point is 231 degrees Celsius. So now 231 degrees Celsius is quite high, right? It is very high boiling point. Molecule has some interesting functional group. So what happens, such a high boiling compound, if you were to heat, if you were to, let's say, try to separate by boiling, uh, boiling the compound and try to receive the compound, vaporizing and collecting the correct compound, then you have to heat it really, really hard. So that's why separation using other methods are not very efficient. It can cause the molecule to dissociate, break down, many things can happen. So chromatographic technique, on the other hand, is fantastic. It is done at room temperature, so you don't have to heat it. Okay. So remember, we have learned distillation in the last semester. Fractional distillation. You separate compounds based on their boiling points, but that is not a good idea for high boiling liquid. So for high boiling liquid, chromatographic method is fantastic because that is totally non-invasive, because you are doing at room temperature. Okay, so therefore there is no destruction, there is no risk. Besides, you separate with extremely pure form. So that is what you are going to be doing. One lab, let's say 1109 will do one, 1113 lab will do the other one. But now here, all of you are here together, so so I'm talking all of them together. Now, separation principle is the same because we are all going to be doing chromatography. Which chromatography you are doing? We are doing column chromatography, right? Column chromatography. I think I have written that at the beginning. We are doing column chromatography. Now, column chromatography in 262, I think you have come across this discussion more in depth, or at least not necessarily in depth, but broadly, classification wise. At least I did when I taught 262. that column chromatography is one aspect of liquid chromatography. There is gas chromatography, there is liquid chromatography, right? You have done this. In liquid chromatography has various branches, right? Where liquid chromatography has various other uh, techniques. What are those other liquid chromatography techniques? Let me quickly indicate those, and then I will go on to the one we are going to be working with. Number one, so LC for liquid chromatography. I think you can now figure that, or if you want, I can write it: liquid chromatography. Liquid. So generally we call it LC. So what are such liquid chromatography? The very best one is column chromatography that we are going to be doing. Let me write that first. Column chromatography. And you have also used another aspect involving liquid chromatography is TLC, right? Thin layer chromatography, right? Thin layer. You have to do that very carefully with your tender loving care. And guess what? TLC also is tender loving care. So you have to use that while you do this. Another thing you have done is flash chromatography, which is the same as adsorption chromatography you did in 262. It's also called flash chromatography. Flash chromatography is what you did adsorption, or your test tube or your toy chromatography. That is flash chromatography. There is another more powerful one that is called HPLC. HPLC. It is called high pressure liquid chromatography. That is in fact, in a sense, more powerful. More principle is the same, but application wise it uses high pressure that results in high performance. Okay, that results in high performance, so that separation becomes more efficient, more effective. Okay, in gas chromatography, you have seen, so this is LC. I also quickly indicate you have did GC. Remember, in GC, you had used a gas, right? I had indicated this thing that in gas chromatography, the mobile phase was gas. Mobile phase was gas. And that gas in particular was helium, right? Helium. It can will be neon, but generally helium. And there was stationary phase. Stationary phase was a liquid. Stationary phase, that was a liquid. And that liquid was some polymeric substance, high boiling, highly viscous liquid polymer. But we are not going to go into that, even though at some point you will be using GCMS later on as part of your analysis. Now, let me quickly indicate the principle one more time. Even though you are supposed to have learned in Organic One lab, I want to make sure that you are very clear about that. For a number of reasons, you definitely want to make sure your concepts are fully clear. Secondly, as I mentioned, everything I talk here, all the theory and principle are part of your syllabus for your midterm and final exam. Therefore, I am not going to be skipping anything. So, what is the principle? So, let me quickly write that. Principle of chromatography. So principle means the underlying principle, the logistics, the reasoning, and etc. I remember it's a funny story. It's many years ago, I think it's more than 20 years ago. I was teaching in George Mason in Virginia. And one student said, "Oh, Professor, you wrote the principle, your spelling is incorrect. It should be principal." I can imagine principal, because she was used to knowing principal, school, college has a, high school has a principal, but that principle has a different meaning, right? So anyhow, so here we're talking about the principle of chromatography. Basically, that is the theory aspect. So what is the fundamental principle behind chromatographic technique? So here, let me write it down very briefly, and in a sense, very composite sense. It's differential distribution. Let me write it this way: differential, or let me, okay, let me write this one. uh, chromatographic technique is based upon, and here I put quotation, uh, differential distribution of compounds in a mixture. Mixture has multiple compounds that will differentiate distribute differentially uh, between two phases. Between two phases. So here is the key term, two phases. What are those two phases? Well, this statement is quite heavy, quite verbose. In a sense, you can see not only distribution, differential distribution. What does that mean? Right? Differential distribution. That's one thing. Then comes the second part, between two phases. What are those two phases? Right? So we need to understand these two phases, and we can see how they distribute, and that distribution will be differential for different molecules, different organic compounds, and thus they get separated. So we need to break down these two phases to understand the whole thing. So the two phases are, first of all, one is stationary phase. Stationary phase, generally it is written first. So stationary phase is something. Stationary actually has another English meaning. You probably know that is in something that is fixed, right? That does not move. Okay, fixed means does not move. Does not move. And this phase is also more polar. This is more polar. Okay, what are these example is these two things are used for in the stationary phase, that is silica. Let me use different color. Why not, right? Silica is actually silicon dioxide. Oxide of silicon, or it can be alumina. Alumina is aluminum oxide, Al2O3. Aluminum oxide is slightly more expensive, um, and between silicon and aluminum is slightly more polar, more metallic, and that is the reason it is slightly more polar also. Only difference, if you are to know, slightly more polar than slightly more polar than silica. So silica or alumina, either one can be used. Most commonly silica, because their functionality is almost identical and does the same job. And most importantly, it is a whole lot cheaper. Alumina being slightly more polar in some specialized cases in research lab, some people may uh, choose alumina over silica in a very few rare cases. Otherwise, silica is most commonly used. It is the most versatile stationary phase, and that is clearly more polar. Second one is mobile phase. Mobile phase. Mobile phase, the meaning, as you understand, something that is mobile, meaning something that moves, something moving. Okay, that is not fixed, it can move. Now to mention that it is also less polar. It can well be even non-polar. Let me write non-polar to less polar compared to stationary phase. What are the examples of some mobile phase? Well, the mobile phase examples are dozens of them. Yeah. All organic solvents are potential mobile phase. However, not all of them are used, but still several dozen of them, or at least a dozen of them can be used. What are the most common one? The very most common one are ethers. Ethers, which are, not to mention, these are organic solvents. These are organic solvents, and as I said, most common ones are ether. Very most common ether is diethyl ether. It can also be tertiary butyl methyl ether. It can also be dichloromethane, CH2Cl2. It can also be ethyl acetate. Ethyl acetate should be written like this, OCH3, that is ethyl acetate. Ethyl acetate is highly polar. It is in fact the other extreme for polarity, and ethers are far less polar. It can well be an alkane. It can well be just an alkane. 1, 2, 3, 4, 5, 6. Usually 6 carbon. Hexane is the most common. 1, 2, 3, 4, 5, 6. Hexane. Hexane itself is a hydrocarbon, can will be a solvent. Right? So hexane, diethyl ether, etc. Hexane is non-polar and ethyl acetate is highly polar. There is another term that you are going to be seeing as you used, that is called uh, uh, petroleum ether. Let me quickly mention that petroleum ether. Few of you were with me in 262. You may have heard me saying this. What is petroleum ether? Well, petroleum ether is a misnomer. It has the word ether. However, petroleum ether has no ether. How funny that can be. Petroleum ether is actually a mixture of hydrocarbons. Mixture of hydrocarbons. So because they are hydrocarbons, it also means it is non-polar, right? So that will be non-polar. So I had indicated in terms of polarity, this one hexane is non-polar, and so are petroleum ethers also non-polar. Petroleum ether has no ether. It is a hydrocarbon mixture. And as you can see, progressively polarity is increased. This is should not say, yeah, you can say more polar or uh, uh, yeah, let me just say more polar. Sometimes there are occasions where, in order to create a solvent that is of very desired polarity, more desired than these substances, pure substances can offer, we can also use a mixed solvent. Occasionally, a mixed solvent is used. Often, this mixed solvent can serve as a mobile phase. Mixed solvent is comprised of, let's say, hydrocarbon, which can be petroleum ether or hexane, hydrocarbon plus ethyl acetate. Because ethyl acetate being more polar, this mixture can give you a desired polarity. How? Because you can control how much the proportion of each one is. You can have 10% ethyl acetate, you can have 30%, you can have 50%, you can have 60%, etc. and etc. So that can also serve as a solvent, as a mobile phase. So mobile phase is moving, which is a liquid organic solvent. Stationary phase is fixed, which is silica. And as I had shown you the column, that column shows just that. Here you can take a look. This column shows inside is silica. You can see white substance, and uh, uh, and liquid is, you cannot see actually liquid. Of course, it's colorless, but liquid is clearly there. Okay, let me show you another diagram. Oops, this one. So here is also a list of solvents going from non-polar to highly polar. Hexane, petroleum ether, benzene. These are least polar or non-polar. Gradually, polarity increases to ethyl acetate. And by the way, the last few, the acetone, ethanol, they are way too polar. They are not used for column. I'm just indicating some solvents, but as you know, water is used for other type of reactions, not in organic reactions often, and those are not used. Usually up to ethyl acetate is the limit. beyond ethyl acetate, acetone and ethanol, they are extremely polar. They are not used. And silica and alumina, here is a picture of that. Silica, as you can see, it is basically sand. Sand is silica. It is the same sand that you see on the beach, except that are not refined. This silica is chemically pure. It has no other impurity, no other minerals, no metals. Therefore, it is completely white crystals. Alumina is very similar, slightly more finer particle than silica, but slightly more ionic. So how the method works, here I'm showing another way of showing a same column. What happens is your stationary phase is is fixed in the column. I'm indicating a column in this symbolic manner. I think that will do the job. Please, can you excuse me for a second? I have to turn off my AC. It's too cold. So in this, I'm back. So here in this picture, you can see here on the very left, if you look at the very left of the five columns on the left hand side, the very left one shows a column, and on the very top, this dark line indicates that here is a mixture of substance that you want to separate, right? You want to separate the components from the mixture that you place on the very top. And the column is filled with the stationary phase, silica. Okay. Of course, at the bottom, you have a stopcock to close it. The actual technicality, how to construct, the TAs are going to show you. I'm going to indicate pretty soon also. And on the very top of or above this sample mixture, this dark line, you add the mobile phase, which is the organic solvent. It is organic solvent is also called eluent. Eluent. The process is kind of an elution, not illusion, elution with an E. So the organic solvent, since the column is vertical, organic solvent will go downward just by gravity. And the stationary phase is fixed. How to fix it, will indicate that soon. So imagine it is fixed. So liquid moves through the stationary phase, going down, and as it goes, it carries the components of the mixture with it. So the substances in the mixture, they are soluble in the stationary, sorry, in the mobile phase, the organic solvent. But solubility is, there is a variation of their solubility. We can say all of them are soluble, which is also a good way to look at it. They are all soluble in the organic solvent. Then how are they going to separate? Because as it moves through the column being ionic or more polar, that will pull some of the substances strongly because of polar attraction. Silica being ionic, there will be ion polar attraction. That attraction will be different with different molecules. Ones that are more strongly attracted by this ion dipole attraction will be held more tightly to the column and will move slowly through the column. Even though our mobile phase tends to wash it downward, but it is being held back by the stationary phase, because stationary phase, by molecular attraction, by ion dipole attraction, it tries to hold it. Okay, so that's why some compounds will be held more tightly or strongly and will move more slowly. The one for which the stationary phase has less attraction, that is going to move faster through the column, because solvent dissolves all of them, that carries along, and stationary phase does not attract as strongly, meaning that will move faster. So distribution, when I use the distribution, you can say distribution of each component, each compound between two phases. It is far more distributed to this mobile phase, the solvent, but it is slightly distributed to the stationary phase because of ion dipole attraction. So that is the distribution part. But that distribution coefficient, if you say that way, that will be different for different molecules because other compound will be held strongly. Distribution coefficient toward the solid will be smaller and will be held back, move slowly. So that is the differential distribution. Distribution of each compound between two phases, between mobile and stationary phase, which is different for different components because different components in the mixture vary in their polarities to some extent. Okay, the one that is so which one is going to move the fastest? Let's say you have a group of compounds. Here I'm showing with three different colors. As you see, red, green. Here it shows two: red, green, and purple, perhaps. So which one do you think will move fastest? If you have a mixture of compounds, which compound will move the fastest? The one that is most polar or one that is least polar? Think about it. Those who are here, if you answer is fine. If not, I'll talk about that also. We have here three people. Anastasia, Danny, MD. Which one do you think is going to move the fastest? The one that is most polar or the one that is least polar? Oh, someone already answered. Danny already said long time ago, it looks like, right? The one that is least polar. Exactly, you are exactly accurate. So the one that is least polar is going to be attracted less by the stationary phase. They're all attracted by the mobile phase, and thus it is going to move faster. Exactly, very correct. And the one that is attracted the most, meaning the one that is most polar, that is going to be the slowest, that will come the last. And that's what you see in the second picture from the top. As you keep liquid moving, it slowly goes downward in gravity. Liquid is moving, flowing downward, which is a process of elution, we can say. And as it moves slowly with time, the components get separated. Initially, they were together. Because of this difference in their attractions towards stationary phase, they move at different rate and they get separated. It is pretty much like a race, right? Race between the compounds. It race of different compounds through this uh, stationary phase, right? So when the one that is fastest come out, you collect them because you have a stopcock. In this picture showing the red one came first, and then you collect. Once you collect in a container or a test tube, you can get rid of the solvent. If you get rid of the solvent, you have your compound, right? In getting rid of solvent, you are going to be using a rotavapor that rotates and evaporates the solvent from the surface. Eventually, solvents go away, leaving the compound behind. Okay, so that way you can retrieve each compound. Here showing red and green. On the right side is showing three different colors, for example. So this is what is a mean by or what is the how the principle works inside a column. So you can also take a look at in this column. Here is a realistic column. Real column on the left, so you see on the very top you have a compound mixture, and the stopcock keeps it closed. And then over a long period of time, on the right picture shows how they got separated. Okay. So a few things comes with this. First of all, you may think, how come the solid will not pass through? And how do we get the solid in? Which is slightly different from how you did the adsorption chromatography, this children's game in Argo 1 lab. There is just stuck in some solid, and that was your column done in a open or is what is it called, in a not even burette, a dropper, right? A plastic dropper you had used. Here you use professional column. So here are some interesting logistics about that. Yeah, first of all, you actually mix the mix the stationary phase silica, you mix the silica in in the mobile phase, the solvent. So solvent and silica are mixed together. Let me write it roughly also. Uh, my drawing may not be as great as yours. So imagine first you have, let's say here you have a beaker, and beaker full you have, let me try to draw some idea of giving, you have some silica here. Okay, this is your silica. And let me label it saying this is your silica. And then you add the organic solvent, the one that you are going to be using for column, you mix with that, you add that. But these two are not going to be miscible because your silica is polar, solid, and your mobile phase organic solvent, that is non-polar, they don't dissolve each other. So you add solvent, your solvent is your mobile phase, you mix together. However, still you can mix sand and water together, right? If you're in a beaker, imagine you are mixing sand and water. They don't dissolve, but they stay together. Why do you do that? When you do that, then it is easier to transfer into the column. Okay, so here you have your silica, silicon dioxide, and your organic solvent. Organic solvent. This has a name. It is called a slash. You make a slash, sh. You make a slash, and then you transfer this slash into the column. Your column, if I can attempt to draw a dumb tube like this, here is a column, and column at the bottom is tapered and has a stopcock here. So my drawing may not be perfect, but that will give you the information you need. So here is your column, and here is a stopcock that goes with that. So you fill up this column. Let me give you a sense here. So you fill up this column with this stationary phase. Actually, you are mixing with the solvent, not dissolving, mixing, creating a slash. They fill up this slash inside this column. It is relatively easy to transfer, uh, and you can also use a glass rod to help work with it, play with it, and move it there. However, I should really warn you before I actually what I did. Let me take it back for a second. For example, sorry about that. Let me indicate this thing. We will do that, but let me mention one more thing. Now, if you are going to add slash like that, what I was showing, you see the risk is you if your stopcock is open, then it is going to flow through. You don't want that. So number of things need to be done. First of all, make sure your stopcock is closed, which you can rotate and close it. Secondly, when you are going to be running the column, when the liquid is going to be continuously moving downward, you want to make sure your slash does not move. And that, to ensure that, you are going to make a plug. You will put a plug at the bottom. This plug can be made up of, so let me just indicate here you have a plug. So what are you going to use to make a plug? Plug can be made sometimes using cotton wool, but it's not a good idea because cotton is also a chemical substance. It has hydrocarbons. Therefore, best way to make the plug is glass wool. Most professional, glass wool. But I remind you, we will not be using glass wool in the lab because using glass wool requires additional precautions. Glass wool is like a cotton ball made up of glass material, very thinly, finely powdered glass. Glass meaning another silica. So what happens is if you have glass such thin, it's not even hair, it's like a cotton, it's extremely thin. So it can easily fly away in the air. And if it flies, it can easily come to your eyes. So you can imagine if it's such a tiny glass particle goes to your eyes, you cannot see it, you cannot remove it, it stays forever. Very dangerous thing to use. So unless you are highly experienced, you don't want to use that. When you have experience, when you use your goggles securely, then it is okay. I had used that many times. You will use in the future also. So you use a plug with glass wool, or in a less professional manner, it can be cotton wool. Cotton wool. So glass wool is the desired one. Why glass wool has another advantage? But why prefer glass wool then, even though dangerous? Can you guess? Glass wool is inert, like glassware. You do reactions on glass because it does not react with your chemicals, right? That's why glass wool would be a perfect thing. Now, this glass wool being a wool, still some some silica may penetrate through. That's why you do some additional precaution, which is on top of that, you put some coarse sand. Coarse sand. That's the sand you know of from the beach. That sand is called coarse sand. So basically, these are larger particle of sand, and they are not, in fact, as refined, but they are beach sand, but still refined chemically, making sure there is no chemical residue left, no organic residue left. That's that sand. So you put one layer of that, and you try to make sure as flat as possible. And on top of that, you add this slash, your silica slash. So slowly work with it. You can tap on it to make sure they are nicely packed. Perfect packing is important. If packing is not well done, if there is air bubble, that can cause some problem. Then your compounds will move non-uniformly and will not create a nice band. Okay? So you don't fill it up, you put it up to certain distance, and then on top of that, again, you put another coarse sand layer. Okay, another coarse sand layer. Here you have again coarse sand, such that it stays a stable bed of your uh, of your stationary phase. And above that, here you will put your solid sample. Here is your sample. Sample itself can be made a thick solution in the solvent, because sample will dissolve the thing. So you can put that also. There are a number of other interesting clever techniques, as you will learn in the lab. Sometimes you can mix the sample compound with the solvent and some silica together and create a mixture like that, and which you place on the top. Best idea would be on top of that you put an additional layer of the coarse sand. That way it stays very fixed. You are sandwiching between two sand layers. Okay, and then uh, yeah, it can stay like that. And then on top of that, you are going to be adding your organic solvent. So here, your organic solvent will be added. So initially, if your stopcock is closed, you're doing all this mixture, you can, time to time, you can open it to make sure your liquid flows through. Liquid is going to drop through, which is fine. Making sure the liquid never goes beyond the sample. There should always be liquid on top of that. Do not let it dry on the top. So liquid now passing through, it is now penetrating through this stationary phase, and this distribution is happening, partitioning is happening, and separating. And as they separate, here goes the other picture I had shown you before. As they separate, you get different bands. Here is two, three different bands. Here is realistic bands like this, and more idealistic band would be like this separate colored band material. Okay, now compounds may or may not be colored, so they may not look so distinctly beautiful, but sometimes one of them is colored, one of them not. Even one is not colored, when they are concentrated in the stationary phase, they kind of look like a area where you can feel that there is some substance creating a band. Like see here on the right hand side, in this picture on the right hand side, you can see there is one kind of band going on there. So that's how they are separated. And you open the stopcock, liquid keeps flowing. Make sure you always have liquid filled in from the top, okay, such that it can continuously flow, continuously separate, and separation occurs. So that is the whole technique. Okay, any questions from you guys? Those who are present by chance? Uh, Let's see. So in the picture you draw, there has to be coarse sand both below and above. That would be idealistic way to do that, and that would be my preferred way of doing that. Your TAs may choose only instead of a sand, they will definitely use coarse sand at the bottom. On the top, they may or may not use coarse sand, depending on how they are trained in their own research lab. These are PhD students. They are knowledgeable. They know what they're doing. So follow their instructions. I would certainly prefer to put coarse sands to make sure that your sample bed is fixed, sandwiched, and not interfering. Especially as you can see from your common sense, you are adding liquid from the top. So if you add liquid, you are disturbing the top, right? As you disturb, if you do not have your sample well trapped, then it can cause some disturbance and it can break the sample layer. If it breaks, then it causes non-uniform and the bands are going to come at an angle rather than straight band. You want to see beautiful band, you don't want to see a sideways band. Sideways band has a term called channeling. You don't want that to happen. You don't want to have any air bubble. You don't want to cause any channeling. You want to have uniform movement as a uniform band. That way, separation, when it comes down, you will be able to separate each layer individually and more accurately. We'll be doing in the lab. Yeah. So when you do the separation, as I said, in your separated component you get, which in your case is going to be your carbon molecule, and then you retrieve uh, in a in a what is it called? Coarse sand, yeah, coarse sand. Any sand is silica, right? Coarse sand is silica. Your fine sand is also silica. Coarse sand is meaning they are just larger particle of sand. Your silica is also sand, except they are exact chemical material wise they are same. Coarse sand is just like a very similar size as the you see on the beach, and the one that you are using in the column they are much more fine and all white color. Coarse sand layers that sandwich the sample pretty much stabilize the sample between the whenever liquid is exactly Anastasia, you are exactly correct. That is the correct thought. Exactly. So let me ask you one question. As you have understood, this is a question regarding the principle that you seem to have understood. When you see that, as I discussed the principle, the compounds are separating based on their polarity, right? The one that is more polar is the slowest. The one that is least polar is going to move out first. So let's say if we have two compounds, they are extremely close in their polarities. The difference is very small difference. Can that be separated or how can that be separated? What would help them to separate? Think for a moment. If the two compounds are extremely close in their polarities, what can be done to make sure they are get separated? That is fantastic, Danny. Exactly. You have to use a longer column. So good answer. Excellent. Just imagine two runners in the sports Olympic. If two guys are extremely fast, you cannot separate them in 100-meter race. Put this the same two guy in a 5,000-meter race. There is going to be many feet of gap between them. So therefore, longer column would help. Perfect. Now, what else can help also? If you do not have a long column, can something else be done? Then how will you separate? So if your column is not long, then of course using a more polar, no, changing polarity of anything does not do any good, because that is going to be the same effect on both of them, right? Whatever solvent you change, that affects equally to both of them, because both of them, the difference between them is small difference in their polarities. So only other answer would be, in that case you are going to have to do this elution for a long period of time, right? Just again, let me allow me to use the same analogy. If 100-meter guys are not separating in time, finishing at the same time, let them go back and forth, back and forth, back and forth for a long period of time on the same 100-meter court. Eventually they will separate. That is equivalent to longer distance, right? So instead of a longer column, if you do not have long column, you can elute for a long period of time, and they will eventually separate. All right. So, these are the conceptual backing. Now, this lab is written in a little bit peculiar way, which has some meaning. Is that your principle is perfectly what I just said. Now, another goal is going to be just actually to indeed to separate the compounds, and indeed to retrieve them, and to analyze them, or to collect them. For that purpose, in the end, you are going to be doing something funny, which initially written this way, and we are going to keep that in. We are going to collect 4 different samples. So first, you are going to, now this is not a correct way to actually do that, because by doing this, it goes against all the principle that I have talked about, right? But that principle is the perfect way to separate things over a period of time, and that period of time can be 1 hour, it can well be 2 hours, etc., etc. But another aspect is to collect the actual compound, and the lab is written by someone who actually was focusing more on getting the compound, as if that is our goal. But I am talking about the principal aspect, what can be applicable for any situation, anytime, anywhere, when you synthesize something. In terms of goal, say this compound is known, so you're going to flash with, this is very crude way of doing that, with 60 milliliter of 100% PET ether, meaning you are doing something with purely non-polar substance, and whatever comes out, collect them. And then next time around, you do a 32 milliliter of 90% PET ether, 10% 9:1 ratio PET ether. I talked about the PET ether hydrocarbon mixture to dichloromethane mixture, CH2Cl2. Okay, this thing actually goes against the principle in some way. Then you do it 25 milliliter of 4:1 mixture of PET ether. So if you're using varied polarity of solvent, so you're changing polarity of solvent different times, only to see which solvent mixture, which polar mixture helped you get one compound. So you're not doing separation. The problem with that is this thing is done as if your goal is only one, you get your natural product from the compound. That should be done in the sense of natural product separation, not, or say extraction from natural source. We know this works, as opposed to unknown substance. In an unknown case, you have to use what I have just talked about so far. In the end, you can use 1:1 molar mixture of PET ether to dichloromethane. When you do that, you are going to see one of this portion is going to have all of your carbon. But that goes against the separation technique. That goes in terms of extraction of a compound from the oil. Do you get my point? But when you synthesize a compound, you have number of other compounds, some impurities. You do not know what their situation is. You will not be doing this. In that case, you will be doing one particular solvent that dissolves all the material. That would be general principle, general theory. This way helps to extract your carbon. In one of these samples is going to have your carbon, and you can see which one it does. Okay. So that's going to be all. And as I said, after you get eluted, then you uh, remove the solvent using rotovapor. That's all. All right, guys. So good luck with the lab tomorrow. I think we are going to have another similar situation 2 other weeks when Monday is off, Tuesday have class, or Tuesday off, Monday has class. I think that may come this month again. So I'll make announcement. I'm thinking, yeah, I'm thinking one of days I'll probably the day we have class on Monday I will give the lecture, but the lab will be done a week later, but it will be saved anyway. All right, so that's about it. So have a good night and good luck with the lab tomorrow. I'll try to stop by in the afternoon. See. Okay, bye bye. All the best. Yes, yes, Anastasia, go ahead. What's your question there? Uh, when you say liquid that you pour on top of the, you're referring to the organic solvent, exactly, which you use to create the slush with. Yes, your your thoughts are correct. Answer is yes to both. Yeah, you make the slush in the same mobile phase, same organic solvent. Yes, yes. You're welcome. All right, see ya. Bye bye. Good night.